When I was a kid, the basic command on my TRS-80 Coco that intrigued me the most was the paint command. It was like a robot with crayons, automatically coloring in any shape I could think of. You simply tell Paint where to start, what color to paint, and what color border it should stay within. Somehow the command figured out the rest, coloring through all the nooks and crannies, but never crossing over the border. It seemed to have a life of its own. It would explore down a path, maybe leave some parts for later, but it would always come back to them. How does it work? Today, jaw-dropping illustrations and sophisticated visualizations developed with powerful emulator scripting unlock the secrets of how 1980s-era computers turned your TV into a coloring book. Prepare for the ride of your life as we solve the mystery of paint. I'll be describing the paint command that came with Extended Color Basic on my TRS-80 Color computer, as well as the basic that shipped with the Dragon computers. Once I learned more about algorithms, I realized that a technique called recursion, along with a basic graph algorithm called depth-first search, could be a simple way to implement paint. But I was totally wrong. Depth-first search is simple, and it works great. In fact, I wrote a version of Paint using depth-first search, which I will show you later. But the real Paint does something else, something more complicated. We'll talk about why they did it the hard way, but first, let's talk about what it's actually doing. The main two pieces are a stack to keep track of all the things it needs to do, and a routine to paint a single line. Imagine you're at the DMV, Department of Motor Vehicles, but this is the worst DMV. It is like the DMV from hell. Actually, it is the DMV from hell. You've just arrived at the underworld, and you need to get your ID. You kind of float in through the entrance, and then glide down until you're lying on the floor. They don't have lines at this DMV. You just lay down on the floor of molten lava until your name is called. But you're not worried, because you arrived early. So you're sure to get out of here really fast. Then another customer glides in, and they gently fall down to rest on top of you. And then someone else comes in, and they do the same thing. It's about now that you happen to look at the ceiling and see this ominous message: first come, last served. Finally, the employee arrives, some kind of dancing demon. He puts on a little show, and then finally he starts helping customers. You're stuck, and you can't move, but that's all by design. Instead, the customer who just came in floats up to have their turn. As time goes by, more and more customers come in and push themselves onto this stack, and are then pulled up in reverse order. This is truly the most unfair customer service experience. You got here early, hoping to leave early, but now it looks like you're going to be here all day. And that is a stack. It's just a list, but when it comes time to pull an item off the list, you pull the item that was most recently pushed on. Rather than first come, first served, it's first come, last served, or last come, first served. The stack is the first main component to understand about the paint algorithm. The other main component of the paint algorithm is the paint line routine. The screen is composed of pixels in a grid. The pixel at the upper left corner has coordinate 0, 0. That's an x-coordinate of 0 and a y-coordinate of 0. As we move to the right, the x-coordinates get bigger. As we move down the screen, the y-coordinates get bigger. If you're familiar with Cartesian coordinates from math, this takes a bit of getting used to, since the y-coordinates get bigger as you go down rather than up. Feel free to pause the video here to rethink your place in the universe. So what is paint line? It's simply a routine to handle painting one line, specifically one horizontal line. Given a coordinate, PaintLine knows how to paint left until it hits a border or the edge of the screen, and then to paint right until it hits a border or an edge of the screen. So how does the full paint algorithm use the PaintLine routine and the stack together? Every time the PaintLine routine finishes painting a single horizontal line, it pushes onto the stack a reminder to do the next horizontal line. Let's run through an example to see how it works. For our example, this is the screen that we're going to paint on, and this is the command we'll use to paint. We'll start at coordinate 2, 2, which is right here. Our paint color will be blue, and our border color will be yellow. So we're going to start outside the figure, and we'll expect that by the time we're done, we'll have painted blue around the whole figure, but not inside. So to get started, we run the PaintLine starting at 2, 2. What that will do is paint left as far as it can go, and then paint right as far as it can go. So it figured out it can actually paint the entire line. Although it looks like the line doesn't extend all the way to the left and all the way to the right, that's just because the TRS-80 Coco has a border that surrounds the active display area, and you can't do any drawing into it. You'll notice that when we finished, we just pushed something onto the stack. That's our next item in our to-do list, and it has us going south, down the screen, from y-coordinate 2 down to y-coordinate 3. You'll also notice that the x-coordinate is now 0. Although we started at x-coordinate 2, after we did the PaintLine routine, we realized we can extend all the way to the left. So on the stack, we're just going to start at the leftmost point of the line we want to paint. But since we're just beginning the algorithm, we're going to do a one-time special deal. Rather than just pushing one item onto the stack, we're going to push a second item. This item has us going north. So this algorithm bootstraps itself by going both south and north after the very first PaintLine is run. Since the north item was pushed last, it's the one we're going to do first. So we're going to go ahead and run the PaintLine routine, starting at coordinate 0, 1. By the way, you may have noticed there's another number in there, 128. Don't worry about it, we'll talk about it later. We go ahead and paint that line, and then for the next thing we push, we continue in our northward journey up to 0, 0. Paint and push, and now it seems to think we're gonna keep on going north until our y-coordinate is -1. But not to worry, as soon as we attempt it, it realizes that that's out of bounds and it will do nothing. That means it can go ahead and pull off the southward entry and go back to 0, 3 and paint that line. And then it pushes the next southward line, 0, 4, paints that, pushes 0, 5, and it continues like that, on and on and on and on. Once it's time to paint the line at y-coordinate 14, same as usual, we push 15, but something different is going to happen now. PaintLine realizes that it runs into yellow, and so it doesn't go all the way to the other side of the screen. But it still goes ahead and pushes 0, 16 to continue its southward journey, and it continues to do this. Once we get to y-coordinate 28, once again PaintLine is going to be stopped short. It can only paint until the yellow border is found. But again, it keeps on going on its way. Painting and pushing, painting and pushing. Once we get to y-coordinate 70, it figures out that it can paint much further and just keeps going until it hits the yellow border. And then it keeps on painting and pushing, all the way down the screen. And unfortunately, it thinks it's done. Remember, we were supposed to paint all of the outside blue, not just part of it. What happened? Well, there's another part of the algorithm I haven't told you about. The border scan. We're going to start off the exact same way that we progressed last time, but something different is going to happen here when y is 15. As usual, we're going to start at the left, we're going to paint the line up until the border, and on the stack, as usual, we add a reminder to continue going down the left side of that border. But now we do a border scan. We peek on the other side of the border. We keep going through yellow until we hit non-yellow, and we realize there was a whole new opening there on the other side, which we just painted. And not only did we just paint it, we added another reminder on the stack to go down the right side of that border. So already we're doing better than before. And since the right side of the border was the last thing we pushed, it's the first thing we're going to do. Go down the right side again. Go down the right side again. We'll keep on doing this until we hit our next border. So once again, we go ahead and run paint line until we hit that border, but then we scan that border to see if there's something on the other side, and oh, there is! We paint that line, and then we add yet another reminder to go down the right side. So now we have reminders to go down the left and right side of that border, and to also go down the left side of the first border we hit. And it just continues in this manner as we go all the way down. Every time we hit a border, we do that scan. And now that we hit the bottom, we have those reminders on the stack to go ahead and go down the other sides of the borders that we had procrastinated doing. First up, it's that second border that we hit, reminding us we need to go down the left side. So we go ahead and paint those lines going down the left side. But then something interesting happens here. We scan that border. And if you're really paying attention, you might be asking, why don't we accidentally start painting on the other side? After all, there is more non-border pixels after this yellow stripe. Luckily, the algorithm is smart enough not to paint to the right of that, and that's where these numbers come in. Let's rewind back and take a look at how those numbers play into this. Every time the algorithm pushes an item onto the stack, it's not only giving us the coordinate and the direction, but it's also giving us this extra number. At the beginning, this extra number always seems to be 128. It turns out 128 is how many pixels it just painted in that paint line. All of these lines up here are exactly 128 pixels wide. But then we run into the border. The 128 tells us that the previous line we were able to paint 128 pixels. So if this next line paints fewer, and in fact we were only able to paint 41 pixels to the left of the border, then that tells us that our painting surface area has contracted from before. It was wide before and suddenly it got shorter. And that's what tells us it's safe to go ahead and scan through that border, but not to go beyond the 128 width. So if we can find some pixels after the border before using up our 128 width of pixels, then it's safe to paint. And if you look at the stack now, you'll see we don't have 128 there anymore. The right side paint line consisted of 53 pixels, and the left side paint line is 41 pixels wide. So as before, let's go down the right side until we hit the next border. That previous line was 53 pixels wide. How wide can we make it before we hit the border? Only 11. That means we haven't used up the full width, so we go ahead and scan the border until we hit the other side, but not going beyond our 53 pixel quota. So now let's continue as we were doing before. When we do the border scan, we know that the previous line was only 23 pixels wide. So as we scan the border, we're not allowed to go beyond 23 pixels. And because of that, we're not going to paint to the right of it because we ran out of our quota. Finally, the left side of the figure gets its turn. That was the first border we encountered, and so of course it's the last border that we're going to complete the painting around. And so we continue as before, going down the left side, dealing with borders as we encounter them, not going beyond our quota. And we're done. But not quite. Remember, this is what we're going for. There is one more case that we need to consider, and that's the overhang. We'll go through the same steps as before, scanning our border when it needs to be scanned, painting lines, pushing work items onto the stack. But something special is about to happen here. The next line we draw is going to be just below that line, and it is going to extend further to the left than the previous line just did. Anytime your next line extends further to the left than the previous line means there's the potential that there's a nook. More space to paint going in the opposite direction from how we were going. So at this point, we've been going south, And as we paint the line, we first extend left and then we'll extend right. But as you can see, as we're extending it left, it went much further. And in fact, there are indeed 2 nooks. So before paint line will extend the current line to the right, it's going to add a work item. A work item to go in the opposite direction, to go back up north, starting here. When we get to that work item, then we'll see if there really was a nook for us to do some more painting. But it's not time to do that yet, because we still have to extend the paint line to go to the right. And when we do that, we add the usual work item to continue going south from there. So we just continue on going south on our merry way, keeping that work item for later. And now it's about to happen again. The very next line extends further left than the previous line, and that means there's the potential for a nook. So we add an opposite direction work item, again another northward work item, starting at the left of that line just to see if there's more stuff around the corner. But, as before, we still have to finish the current paint line, so we extend that right, and that gives us another work item to continue going south. Once we've gone all the way to the end, then we can start taking a look at our stack. The most recent potential nook that we found is this one. So we're going to start painting at x-coordinate 0, and that's going to induce a border scan. And as we do the border scan, we found yet another series of pixels that we need to paint. And now that our current direction is north, every time we find more stuff to paint, we keep on painting them up north. So we continue doing the usual stuff until it happens again. And if you understand this, then you understand everything about overhangs. We're in the mirror image of before, where instead of the line extending further to the left than the previous, this line here is now extending further to the right than the previous, and that means there is the potential for an overhang to the right, going in the opposite direction, which now would be south. But as we look at the picture, there is no nook. But the thing is that the algorithm doesn't know that until it explores it. So it's going to go ahead and push a new work item going south, going back down, starting here. And it's not until it actually does that work item that it will realize, oh, that was a false alarm. There actually was no nook there. And then we work back to the next work item. This has us continuing our northward journey on the left side, doing border scans along the way, continuing to paint things up north. And then we stop when we find yet another potential overhang. This line extended further to the right than the previous one, and that means that if we headed back down south, there might be a nook to fill in, and in fact, there is. So we add the work item, and then it's time to explore that. And finally, we reach the first overhang that we found. So we can do that work item and fill in those holes going back up north. And in this way, the algorithm continues until we have reached the end. It's just that simple. Now you might be thinking, sure, that worked fine for that simple example where every angle is 90 degrees. But what about diagonal lines or curves? Well, of course, those work too. Because when everything is made of pixels, every angle is 90 degrees. You never really get smooth diagonals or curves, you just get staircases.
There is no spoon.
I mentioned before that there's a much simpler approach they could have used called depth first search. In fact, it's so simple, I can describe it in just a few steps. Add the starting pixel to your stack. Then continuously pull a pixel off the stack, paint it, and then push the 4 pixels around it back onto the stack. Repeat. Just be careful that if you pull a pixel off the stack that you already painted, or that is the border color, ignore it and don't add any of its neighbors to the stack. That's it. That's the whole thing. There's no border scan, no overhangs to worry about. There isn't even a paint line routine. You just go pixel by pixel, pushing its neighbors as you go, and the stack handles the rest. And it works great. You don't need to understand any of this, but just to give you an idea of how much code we're talking about, This is the code for the paint algorithm actually used by BASIC. And here's the code I wrote to paint with depth-first search. Let's try out depth-first search. It works great! So why on earth did they do it the hard way? Well, I did kind of cheat by using a small example. Let's try something a bit larger. Whoa, what happened there? Let's run it again, but show what our stack looks like as we run through it. And here you see there are so many things to push onto the stack that it just grows out of control. If we had enough memory, we could deal with this just fine, and eventually the stack would shrink back down as more and more of the shape gets painted. But we're very limited on these older machines, so we quickly gobble up all our available memory and it go boom! In fact, what you're seeing is the stack literally encroaching on video memory as it grows out of control. And if we run the shorter sample, we'll see the stack also grows huge, but not so huge that it overflows other memory before the algorithm has a chance to pull off all the work items and finish the paint. So the paint algorithm that the developers of Extended Color Basic used is a highly customized and optimized way to paint the pixels within a border while keeping our memory usage under control. Formally, it's considered an optimized variant of the span filling algorithm. For some of you, that was more than enough, and congratulations for making it this far. But for others, you may still have some questions. Like, was there any advantage to using a stack, which reverses the order of how we proceed through the shape, as opposed to just using a regular list, first come, first served style? Or maybe you're curious what kinds of nifty assembly language programming tricks I discovered while analyzing the paint code. Or maybe you'd like me to come clean about all the things that I simplified for the purposes of this video so you can see what's really going on. Or maybe you'd like to see how I instrumented the code and scripted the emulator to animate the stack. Look for an upcoming video where I do a deeper dive into all the technical details of the paint implementation. Until then, thank you for watching. Feel free to pause the video here and take some time to contemplate your plate. Darn it. If you're familiar with Cartesian coordinates from math, this takes a bit of use. Feel free to pause the video here to rethink your place in the universe. Since the y-coordinates here get bigger as you go down rather than up. Not even that funny. Hi ho ha ha. Ho hey hi ho hi. Look for an upcoming video. Time to pull an item off the list. You pull the most recently item that was pushed onto the list, rather than, can't believe I finally got that.